Hello everyone, I'm Chen Xiaoyu from the Nanjing University. Today I will talk about our recent work on the uniqueness and rapid mixing in the bipartite hardcore model. This is a joint work with Jin Chen and Yitong. Sampling from high-dimensional joint distribution is a fundamental computational task, especially for a class of distribution known as the Gibbs distribution. It could be described by only few parameters and local interactions. There is a very interesting phenomenon on the Gibbs distribution known as the computational phase transition, which says that the computational complexity of sampling problem changes sharply around certain parameter values. An important example is the hardcore model. The hardcore model is defined by a graph G and the fugacity lambda. The graph has n vertices and the maximum degree is delta. The hardcore model defines a Gibbs distribution mu, which is supported on all the independent sets of G. Each independent set appears with probability proportional to lambda to the size of the independent set. For example, in the last figure, there is an independent set of size 2, and this independent set should appear with probability proportional to lambda square. The hardcore model has certain phase transition phenomena. Let's consider the hardcore model on general graph with maximum degree delta. And there is a unique threshold, lambda c, which approximately equals to E over delta. It has been shown that for every graph G of maximum degree delta and a vertex V, the marginal probability of V that does not affected by a pinning at distance L as L goes to infinity if and only if lambda is larger than lambda c. This is known as the unique, non-unique phase transition of the hardcore model. The worst case happens at the regular tree, so the uniqueness is also called tree uniqueness. And exactly on the same critical threshold, there is a computational phase transition phenomenon for the hardcore model. When lambda is larger than lambda c, White has showed that there is a polynomial time algorithm to sampling from the hardcore distribution. When lambda is larger than lambda c, slides show that there is no polynomial time algorithm unless NP equals to RP. The intuition of the hardness result comes from the fact that when lambda goes to infinity, then sampling from the hardcore distribution is equivalent to sampling from the maximum independent set in the graph G uniformly. This is very hard since even find the maximum independent set in a graph is hard. And in this work, we attack the same problem of sampling from the hardcore model. The difference is that we restrict the graph to be a bipartite graph. And this problem has a very famous special case known as the sharp base problem. It happens if you fix the fugacity lambda to be exactly 1. The biggest issue of this problem is that the previous hardness result that applies to the general graph does not apply to the bipartite graph. This is because, by a famous result, there is a polynomial time algorithm that could find the maximum independent set in the bipartite graph. However, this problem is also hard in the sense that there are many important problems that people do not know how to solve them could be reduced to sharp base by reduction. So previously, it has been conjectured that the sharp base problem represents an intermediate complexity class, which means that it should has no polynomial time algorithm, but it should be easier than the counting version of the satisfaction problem. There are many previous work that attack this problem, trying to give efficient algorithms. These works could be separated into two types. The first type is the algorithms that works in the non-uniqueness regime. This type of algorithm often needs special requirements on the bipartite graph. For example, they may need the graph to be an expander, regular, random, or unbalanced. Another type is the algorithm that work in the uniqueness regime. Actually, an easy result could be made by noticing that the bipartite hardcore model is a special case of the general graph. But apart from that, as far as we know, there is only one result that could work in the uniqueness regime. In LL15, they consider a special case where lambda equals to 1, and when in the uniqueness regime, they have an efficient sampling algorithm. The difference from the general graph is that the degree bound of their assumption is only made on one side of the bipartition. This regime is weaker than the uniqueness regime for the general graph, since the degree on the right side could be unbounded. We want to go further and extend this to every positive lambda. And the only advantage that we would use is that the graph family required by the weak spatial mixing here is restricted to the bipartite graph with degree bound only on one side. After some investigation, we find that the worst case for the weak spatial mixing is achieved on the DW array tree. This means each node in the even level of the tree have D children, and node in odd level of the tree have W children. And the node on even and odd level of the tree forms different side of the bipartite graph. And we use even level to denote the side with degree bound and with an odd level for side with unbounded degree. And due to the symmetric structure of such tree, we could give a two-level tree recursion of marginal ratio on this tree, which means if you tell it the marginal ratio of the grandchildren of the subtree, then it gives you the marginal ratio of the root. So if you are familiar with the tree recursion of the hardcore model, you would easily find that this recursion is a composition of two tree recursion of the hardcore model. So whether this system has weak spatial mixing is equivalent to whether the fixed point iteration of this recursion eventually converges to its unique fixed point. It is easy to see that when the recursion have multiple fixed points, it fails to converge, and when it only has one fixed point, it eventually converges. Moreover, the long-term converge speed is controlled by the derivative at the fixed point. So it is natural for us to define the following notion of delta uniqueness for this model. It requires the first derivative of the recursion to be smaller than 1 minus delta at the fixed point. The small delta here is used to control the converge speed. We let W to be arbitrary since we want to remove the degree bound on the odd levels. Okay. So now we have a precise definition of what means delta unique. This definition of delta unique itself is very hard to use, since it only tells you some implicit information about the parameters using the fixed point. So our first result is a translation of this definition, which makes the uniqueness more intuitive to be understood by humans. If delta, which is d plus 1, is greater than 3, and lambda less than 1 minus delta times lambda c, then the system is delta over 10 unique. This generalizes the result in LL15. It roughly says that the hardcore model on the bipartite graph is unique if lambda is smaller than lambda c. But the degree bound delta here only applies to one side of the bipartite graph. Our second result gives a near linear time sampler for the bipartite hardcore model in the uniqueness regime. And the degree bound only applies to the left-hand side of the bipartite graph. And I should mention that in this model, the degree bound delta L makes a lot of difference. When lambda L is 1, then the graph becomes a forest and the sampling problems become trivial. And when delta L is 2, then the phase transition of the weak spatial mixing disappears, and this model could be reduced to a ferromagnetic Ising model. And besides the fast algorithm, we also have the mixing time result for the Glauber dynamics in the uniqueness regime. The Glauber dynamics is the canonical sampling algorithm for the Gibbs distribution. It is a Markov chain. It starts from an arbitrary independent set x0, and in each step, it picks a vertex uniformly at random. Then, it generates a new state to the chosen vertex by flipping the coin with probability lambda over 1 plus lambda. If the update is feasible, then the Glauber dynamics accept it. And if the update is not feasible, then the Glauber dynamics simply drops it. The Glauber dynamics will eventually converge to the Gibbs distribution. The mixing time of a Markov chain is the first time that it achieves certain error bound. Here, the error is measured by the standard total variation distance. For the bipartite hardcore model, our mixing time bound has a similar form as the running time of the algorithm on previous page, but it has an extra factor of n squared. Okay, so in the rest part of this talk, I will first introduce some backgrounds to you. Then I will briefly outline the proof of the results that I have mentioned, including the fast sampler and the fast mixing of the Glauber dynamics. Let's forget about the hardcore model for a moment and just consider an abstract high-dimensional joint distribution over the hypercube. The Gibbs distribution of the hardcore model is a distribution over the subsets, but we could also view it as a distribution over the hypercube by using +1 to indicate that some vertex is in the subset. We note that there are two nature operations on the distribution nu. First, we could impose an external field on nu that gets a new distribution theta times nu. And this new distribution biases the original distribution nu by adding an extra factor determined by theta and the number of positive coordinates in the vector sigma. And as an example, suppose mu is the Gibbs distribution of the hardcore model with fugacity lambda, then theta times mu is the Gibbs distribution of the hardcore model with fugacity theta times lambda. Another operation is to flip the distribution nu by exchanging the meaning of -1 and +1. The new distribution nu bar is essentially the same distribution as nu. The main algorithmic tool that we would use is the field dynamics. It is a Markov chain. Given the positive parameter theta, we could define the field dynamics for nu. Before it starts, it would pick a flag s from -1 or +1 to make sure that theta to the power of s is smaller than 1. And in each step, the field dynamics will first generate a random subset of coordinates r by adding each coordinates I with value s to r with probability 1 minus theta to the power of s. Then, the field dynamics resamples the rest of the coordinates according to the distribution theta times nu, conditioning on the coordinates in R to be set to S. And surprisingly, as proved by a previous work, this Markov chain actually converges to the distribution nu. So if we could prove the rapid mixing of the field dynamics, and we could find an efficient sampler for the distribution theta times nu, then we could implement the field dynamics efficiently. And therefore, we have an efficient sampler for the distribution nu. Okay. And previously, there are many works that implement this idea formally, and the result of this kind is refined again and again. Here we just pick a version that meets our practical needs. So there are 3 requirements. The first 2 requirements says that for all lambda between theta and 1, the distribution lambda times nu should be k marginally stable and eta spectrally independent. I will further explain these notions later. I also need the Glauber dynamics on distribution theta times nu to mix this in time O tilde n. The first two requirements implies the mixing of the field dynamics. Together with the third requirement, we have a fast sampler for the distribution nu. And actually we could go further and bound the mixing time of the Glauber dynamics by a comparison argument between the Markov chains. However, since this comparison is done via the notion of variance decay, the final result on the mixing time will have an extra factor of O tilde n. Now we give a brief introduction to the notion of spectral independence and marginal stability. Recall that nu is the distribution on the hypercube, and let's say x is a random vector sampled from nu. To introduce the notion of spectral independence, I should first introduce the influence matrix. The ith row and the jth column of the influence matrix is just a subtraction of the marginal probability on the jth coordinate with different conditions on the ith coordinate. This is also known as the influence from I to j. And it is straightforward to verify that the influence from I to j is actually a normalized covariance between xi and xj. And the influence matrix is similar to the correlation matrix of the random vector x. Then, nu is said to be eta spectrally independent if for any feasible pinning tau, the infinity norm of the influence matrix of the conditional distribution nu tau is bounded by eta. K marginal stability actually requires that for every coordinate I and any pinning, the probability that the coordinate I takes -1 will not be too small. And the marginal ratio on the coordinate I will not become too large if we pin more coordinates. So if this holds for either nu or nu bar, then we say that the distribution nu is k marginally stable. Okay, now we are able to outline the proof of our result. And before we start that, let's consider a small example. So there are n vertices on the left and only one vertex on the right. And remember that to make the field dynamics mix rapidly, we need spectral independence. However, if we consider the infinity norm of psi mu, we will find that it could be of order n. So what could we do? The observation is that if you remove the vertex v and only consider the vertices on the left, then the infinity norm is bounded. Here, the distribution mu L is obtained by projecting the Gibbs distribution mu onto the variables on the left. So our strategy is to set the distribution nu to be mu L and run the field dynamics on this distribution. To get a fast sampler on the distribution nu, we only need to verify the three requirements. This would give, we set the parameter theta to be of order theta delta log n over lambda, which is greater than 1. So now if we are able to verify all these three requirements, then this would give us a fast sampler for the distribution nu. Also, we have the Glauber dynamics on the distribution nu to be rapidly mixing. And suppose we could generate random samples from nu, we could also generate samples from mu. This is because once we fix the variables on the left-hand side, then the variables on the right-hand side becomes independent to each other, and they could be sampled easily. So the last two requirements are relatively easy to verify. The marginal stability could be verified by a direct calculation, and the rapid mixing of the Glauber dynamics on theta times nu could be proved by a coupling-based argument. Now we only need to verify the spectral independence. To verify the spectral independence, we have the following result, which roughly says that the spectral independence is guaranteed by the uniqueness regime. And since we have imposed an external field on the distribution nu, we need to consider the bipartite hardcore model with different fugacities on both sides. Let's call them lambda and alpha. If we fix the maximum degree on the left-hand side, then the uniqueness regime in terms of lambda and alpha looks like this plot. The boundary of this uniqueness regime is described by this parametric curve. You could notice that this curve has a very good form, so that if we ask lambda and alpha to be the same, then the uniqueness regime would become lambda smaller than lambda c, which is stated in our first result. So since the model, the bipartite hardcore model with fugacity lambda and lambda is in the uniqueness regime, we know that all the bipartite hardcore model along this line are also in the uniqueness regime, since they have a larger fugacity on the left-hand side. So by this result, we know that all the distribution along this line are spectral independence. Okay. Now we will prove the rapid mixing of the Glauber dynamics on mu. Remember that we have proved the mixing of the Glauber dynamics on the distribution nu. And actually there is a block dynamics on the Gibbs distribution mu that works essentially the same as the Glauber dynamics on nu. It picks a vertex from the left uniformly at random, and it updates it with all the vertices on the right together. And we will prove the rapid mixing for the Glauber dynamics on mu via a comparison argument between this block dynamics and the Glauber dynamics. And in order to do the comparison, we will first consider a sampling algorithm that simulates this block dynamics, but with the restriction that this algorithm updates each site separately. And in an update of this block dynamics, since other vertices on the left is fixed, the vertices that we need to resample will break up into several isolated parts. So there are many isolated vertices and a star, and we know that this star has a degree bound. So we could update each isolated vertices separately, and then we'll run the Glauber dynamics for O tilde delta step to perform an update on this star. And by doing so, we have a fast algorithm to sample from the distribution mu. And since this algorithm updates each site separately, we could compare it with the Glauber dynamics on mu directly by comparing the update rate on each vertex. And in each round of this algorithm, the update rate for every vertex on the right is about to be 1. However, in the Glauber dynamics, every vertex on the right would be updated with rate 1/n. So the mixing time of the Glauber dynamics may have an extra factor of n than this algorithm. So this high-level idea could be implemented rigorously by the notion of block factorization. Okay. Now we only left to prove the spectral independence of nu in the uniqueness regime. So suppose we have a bipartite hardcore model with lambda and alpha be its fugacity, and it is delta unique. We need to bound the spectral independence of the distribution nu. By the previous result on the construction of the self-avoiding work tree and by selecting a special potential function, the worst case is reduced to the d+1 w+1 regular tree. The potential function is log 1 plus x, and its derivative is 1 over 1 plus x times log 1 plus x. For simplicity here, we just work on the dw array tree. And this trees only differ at the root, and this difference could be handled by some small tricks. So now, suppose the root is at the left side, and we only need to bound the total influence from the root to all the other vertices on the left-hand side of the bipartite graph. And they are the nodes that are on the even level of the tree. And according to the analysis in CLV21, the total influence from the root to a specific level 2L is bounded by some constant times the worst case derivative of the recursion f warping by this potential function to the power of n. And suppose this quantity is bounded by 1 minus delta, the total influence would be of order 1 over small delta. So we actually reduced the task of bounding the total influence to a precisely defined mathematical problem that is given the parameter lambda d and alpha to be delta unique. The function h is bounded by 1 minus delta. And for simplicity, here let us just consider this problem for a special case where delta is 0. This would help us to hide some annoying details. And we actually need 3 observations to finish the proof. First, we note that the parameter w could be eliminated by a change of variable that appears in LL15. And as we can see, there is no parameter w in this new objective function u. And this means the choice of w does not affect the optimal value of the function h. And besides, the function u is monotone on the parameter lambda and alpha. And second, we find the derivative of h actually has a very nice form. Here, the function c1 and c2 are just 2 positive functions when x is positive. So why does these 2 observations could help us prove the contraction? Let's look at the uniqueness regime. By the first observation, for every point of lambda alpha in the uniqueness regime, we can move it to the boundary of the uniqueness regime by increasing alpha. And by the monotonicity of the function u, this movement will only make the objective value of this optimization problem to be larger, which is no harm to us. Here, since now we are at the boundary, we know that the alpha and lambda should satisfy this parametric curve. And here, a different statement of this parametric curve actually makes everything work together. It says that for every lambda alpha on the boundary, there is a unique w such that the fixed point alpha d and w would satisfy this system. The first equation of this system actually means the derivative at the fixed point of the recursion f is exactly 1. And the second equation in this system has a very similar form to this function in f prime, in h prime. Okay. Now we are able to prove the contraction. And actually this could be done by a very simple argument. And suppose lambda alpha are on the boundary and let w be wc. Now we only need to bound the value of the function h. First, we evaluate the function h in a neighborhood around x hat. By definition, hx hat is f prime x hat, which is 1. by this which holds by this equation. Now, by definition, since hx hat is 1, we know that the first term of h prime x hat is 0. And by this equation, we know that the second term of the h prime x hat is also 0. So this means h prime x hat is 0. And for the second derivative of h, by a similar argument, we'll find that it actually equals to c2 times the first derivative of this function at x hat, which is smaller than 0. So in a sufficiently small neighbor of x hat, the function h should look like this. Now, if h equals to 1 at the right of x hat, then we know that h prime at this point should be greater or equal to 0. However, by the definition of x hat, we also know that h hat equals to c2 times this function at this point, which is smaller than 0. So this makes a contradiction. And by a very similar argument, we could also show that h should not exist 1 on the left-hand side of x hat. So h should be smaller than 1 for every x greater than 0, except x hat. The main difficulty in this proof is to find a correct form of h prime and the correct form for the boundary of the uniqueness regime, so that the restriction given by the uniqueness regime could be precisely used to bound the function h. And when delta is greater than 0, a similar proof could be done by following the same high-level plane. However, here the correct form of h prime and the boundary of the uniqueness regime becomes even more complex. And an interesting thing in this proof is that since we could pick an arbitrary w here, we could always make sure that the worst case of the function h happens exactly at the fixed point. This is different from the usual situation when proving the contraction. And this really helps us simplify the proof, since we only need to apply the calculation at the fixed point. And finally, we're only left to show how to translate the delta uniqueness condition into a system like this or this. Okay. So recall that the uniqueness condition is a condition at the fixed point, which makes it very hard to use. And since we consider different fugacity on the left and right side of the bipartite graph, we can make sure that there is no lambda in the outer brackets of the recursion. So in this recursion, for a tuple x hat d alpha w, there is a unique lambda to make sure that x hat is a fixed point of this recursion. And so instead of resolving the uniqueness regime in terms of lambda d alpha w, we could first resolve the uniqueness regime on the coordinates x hat d alpha w, and then we translate the result back to the coordinates lambda d alpha and w. Okay. And in this new coordinate system, the condition that f prime at x hat should be smaller than 1 minus delta is equivalent to that the function t delta at x hat is greater than 0. Okay. And a typical case of t delta is illustrated in this figure. We could see that x should be smaller than x delta 1, or it should be greater than x delta 2. And then we translate the regime of x to the regime of lambda, and we know that lambda should be smaller than lambda delta 1 or be greater than lambda delta 2. And also we do not want the recursion to have more than one fixed point. So we also want lambda to be smaller than lambda 0, 2, or to be bigger than lambda 0, 1. Okay. And the number of roots of the function t delta and t0 varies as w goes from 0 to infinity. And the scenario is illustrated in this figure. As w becomes bigger and bigger, the function t delta and t0 will suddenly have a root, and they would give us some banded intervals of the parameter lambda. And after some investigation, we find that all these functions, lambda delta I, would go to 0 as w goes to infinity. So all these banded intervals will eventually converge to a single maximum value of lambda delta 2, which is lambda delta 2c. And this means the smallest feasible value of lambda is lambda delta 2c. And this also means that when lambda equals to lambda delta 2c, then we're on the boundary of the uniqueness regime. So the system that we used to prove the contraction actually arises here. If you set up it like this, the first equation ensures that f prime x hat is exactly equals to 1 minus delta. And the second equation ensures that the function lambda delta 2 is maximized. And in this system, there is a special case. If we let delta equals to 0, then we could solve it, and we could get the parametric curve of lambda and alpha that we have mentioned before. Okay. And in last page, there are some open problems related to this work, and we want to improve the running time of the sampling algorithm or the mixing time of the Glauber dynamics of this problem. And we also want to understand the bipartite hardcore model with negative lambda, since this is closely related to the Schöner bound for the Lovász local lemma. That's all. Thank you.